Hey, welcome to Karen's Lab. I'm so excited to be here today. It's been a while since I recorded the last video. I've been quite busy at the university, but we are back. The summer just started, and I love to swim. How many of you love to swim? So I decided that for this first video of the summer, we're going to talk about rheology. Rheology is the branch of physics that studies flow. Rheo means river or flow, and ology means the study of. In rheology, the most basic concept is the viscosity. The viscosity is commonly represented by eta, and the viscosity means the resistance of the material to flow. Water has very little resistance to flow. That's why you can swim easily in the pool. How about if you fill the pool with honey or with any other materials? It would be harder to swim in there. That means they have higher viscosity. When we talk about Newtonian fluids, we talk about fluids that their viscosity under ordinary conditions is not going to change no matter how fast you force it to flow. We can represent this in a viscosity curve. In the y-axis we have viscosity, and in the x-axis we have the shear rate, meaning how fast we're forcing the material to flow. The viscosity will be constant, it will not change. If we have a material with higher viscosity, for example honey, the viscosity will be higher, but still Newtonian. It still doesn't change, just like water. How about if we have change in viscosity? That would be a non-Newtonian fluid. In non-Newtonian fluids, the viscosity is going to change depending on the shear rate. If it goes up, it's called a dilatant fluid. If it goes down, it's called a celloplastic fluid. Why do we care about rheology? Why is this important for us? What can we invent with this knowledge? Is it only about the water and how it flows and the honey and how it flows? Of course not. There's a lot more. Wait, I'm getting a little hungry. How many of you like pudding? I love pudding. Nice, cool pudding. Cool. Do you want some? Hold on, let me finish it. Delicious. Why do you like pudding? Is it the flavor or is it the texture in your mouth? Try this pudding. I heat it up a little bit. Drink it like that, just liquidy? That's not something that I would try. Same thing, for example, with yogurt. I love the Chobani yogurt. Who doesn't? Same thing, great texture. I'm not saying the flavor is not good. The texture is perfect. And it is because of the rheology. You find the perfect combination of rheological properties. That is the viscosity, that we talk about it, and the other factor is the elasticity. So you find the perfect combination of the viscoelastic properties that it gives you that nice texture. Let's give you some examples of dilatant and celloplastic. The celloplastic, for example, ketchup. What happens when you try to put some on your fries? You turn the bottle upside down, squeeze it, nothing comes out, squeeze it, nothing comes out, and then everything flows out. That is a celloplastic behavior. The viscosity decreases upon the applied force. How about a dilatant material? It's actually a lot of fun. Let's play a little bit with it. For this one, we need some cornstarch. You can buy any brand. We place the cornstarch in a container and we add some water. We mix it well, and now it's time to play with it. I'm applying some force, and the viscosity is increasing. This is called a dilatant. This is a non-Newtonian fluid. This one has a strong dependence with time. What happens if I stop applying the force? It flows, right? It goes back into the container. Now I can take another one again. As long as I apply a force and I move my fingers fast, you can see it act as a solid. The viscosity is really high. And I can try making a bigger ball. And again, as soon as I stop, it flows back into the container. This is so cool. This is like moving sands. Videos out there where people have placed kilograms, hundreds of kilograms of cornstarch, and they have made kind of like a small swimming pool, and they go on a bike, they jump, they move. See, if I hit it, I'm applying force,
It's like a solid.
I can have one of my Lego pieces and it can walk on top and nothing will happen. But how about if I don't use force? Sinking, 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 sinking. If I pull fast, I can't get him out. But how about if I pull slowly? Play with it. It's a nice activity for the summer. But when you play with it, think about the applications that are driven by rheology. Inkjet printers, asphalt, food, in the plastic industry. If I'm making, for example, Lego figures, I have to produce them with the right parameters that will give me a quality product. And that's what I do a lot of rheological studies. See you next time!